Hello everyone, this is me Sadat from Arcanine Game Studios. In today's tutorial, we're going to show you how to create this procedural cloud in Godot engine. Now, as always, I'm using the GLES2 rendering pipeline, which means I cannot use the shader-based particle system. So the only option for me was to use a CPU-based particle system with a custom shader for the clouds. Now, with this kind of approach, you will see some artifacts and some defects in the clouds because this is not a true volumetric cloud system. However, this is the recommended way to go for low-end devices and for mobile games because volumetric rendering takes quite a lot of GPU processing power, and low-end devices just don't have that. So anyways, let's show you what I'm doing here. I'm actually using a very small amount of particles. As you can see, I've reduced everything down to just rendering 64,000 vertices for the entire environment. It can be reduced even further, but I think this is good enough for my purposes. I'm just using 64 particles. You can reduce it down to any amount you want. In fact, you can easily get a very good amount even with 32 particles. I'll increase the speed scale for a moment just to get everything visible again. And you still have good enough clouds in the sky. Alright, so I'm using a sphere for this. You can generate your own spheres and bring in some better models. This might make it look better, but since it's a low resolution shader, I'm using a very small vertex count for each of these. So it's about 8 vertices in the radial segment and 4 rings. So it's a very small shape. You can obviously improve the quality by increasing the number of vertices. Like as you can see, it already improves the quality significantly, but it also increases a significant amount of vertices. So let's go back to this. Alright, so what I'm doing is I'm generating it from 6 points. They're spaced out for between x10 and x0, z10, z-10 and z0. Keeping the y-axis aligned and rotating it on the y-axis only. And you basically play around with the values of the velocity and the gravity and everything to make your cloud look a bit more realistic. But the interesting thing here is in the shader of the cloud. Now, since I cannot use a particle shader, the only option for me was to use a spatial shader. So I used a spatial shader for each of these meshes that you see over here, and in here I'm using 3 noise textures. Now, the reason I'm using noise textures is that computing these noises individually in your shader code is going to be very computationally expensive. And since this cloud is not going to be a very computationally expensive cloud, we're not going to generate this. Instead, we're using a pre-made noise texture, and I'm using a little trick here to improve the noise functionality a little bit. So I'm adding octaves to it programmatically. So I'll show you how to do that here. So this is where I'm taking the noise and converting it into a 3-octave noise function. So what I'm doing is I'm actually sampling each and every texture 3 times. The first time I'm not wrapping it any times more than 1. The second time it's 2 wraps, and the third one it's 4 wraps. So every single sampling would reduce the size of the noise by 2. So this is actually changing the period value of the noise. And I'm storing these 3 period values in the 3 channels of a vector 3. So X, Y, and Z channels. Now after that, what I'm doing is I'm sampling all of these 3 noises, converting them into noise octaves, and then I'm mixing them together in here in this function, which is get mixed noise. Now in this function, the first thing I'm doing is I'm taking noise A, I'm adding the first octave, adding the persistence, which in this case is 0.5, and then adding the persistence, which is 1/4 for the third octave. And then I'm dividing everything by 1.75, which is the added cumulative of the entire value. So this is 1 plus 0.5 plus 0.25, which is 1.75. So normalizing the noise. I'm doing the same procedure for noise B and noise C. Now finally, when I'm combining the noise, I'm actually combining the noise in a priority basis. So the whirly noise takes the most priority, which adds 100% value. The Perlin noise adds 50% value on top of the Worley noise, and the blue noise adds 25% value on top of the Worley and Perlin noise. And then again normalizing it by dividing by 1.75. Alright, so let's see what we're doing in the vertex. We're adding a simple displacement here, which is take the values of the noise octaves, mix the noise together, get an intensity value, and extrude the vertex along the normal by the intensity value and the amplification, which we're setting over here. So if I change the amplification, you'll see that the clouds become bigger. If I reduce the amplification, the clouds become smaller. Right. So now in the fragment function, this is the same function as the vertex. We're taking the values of the noises, converting that into intensity. Now this is where we're adding a little bit of a bump mapping to the normal. So what we're doing is we're increasing or shrinking the Z value of the normal based on the intensity value and the amplitude. What this does is it actually forces the normal to renormalize itself and create a sort of a dent or an extrusion along the normal. So this is a very simplified format of normal mapping. It's called bump mapping. You can look it up. You can use it with pretty much any texture and it will give you a pseudo normal map value to it. It's not the best way to go about it, but you can get started. Alright, so after that I'm just adding the color, which is found here, and setting the alpha to be the intensity value. So the brighter the cloud, the more the alpha should be. Right. Now this is where things get a bit interesting. This is a base fade function. What it does is it actually calculates the distance of the viewing angle from the normal. So how do we figure this out? Okay. The normals in this vertices are all projection space normals. So the Z value will always be pointing towards the camera. Now, the further the angle deviates from the camera, the Z value will become smaller and smaller. And when it's staring directly into the camera, it's going to be the largest, which is 1. So what I'm doing is I'm taking that value of Z, squaring it to the power of 4. What this does is it creates a very sharper contrast between the brighter and the darker areas, which allows me to have more volume in my clouds. So I'll show you. If I reduce it down to 2, you'll see that the clouds look a lot flatter and with less volume. If I increase it up to 8, the clouds seem to have more volume. Obviously they are smaller, they are a lot smoother, but they seem to have more volume. So this is what the power function does here, and I'm clamping it to between 0 and 1. And now I'm setting the alpha to be a smooth step or a smooth mean between 0 and 1 based on the base fade, which gives it that smoother cutoff. And then multiplying by global transparency value, which I'm using to basically increase or decrease the intensity of the clouds. And for now, let's keep it at 1.5. Alright, so now this is where the light function is. This is where we had to make a little interesting change here. Now, normally what we do is for the n.l function, I'll show you what the general n.l function is, which is dot product of normal and light. So with this n.l function, lighting is applied naturally to the clouds. If it's facing away from the light, it will not be lit. If it's facing towards the light directly, it will be lit. However, since clouds allow some light to pass through them, we made a little change here. So let me just go back to the previous one. So what we're doing is we're taking the absolute value, which means Even if the value goes to a negative value, as we know the dot product does, it will still remain in the positive spectrum. So it goes from 1 to 0 and then from 0 to 1 again, even if it's in the opposite direction. So that's why we see that light coming in even if we're looking straight from behind the cloud. And then we're subtracting it by 1. So what we're doing is we're shifting the intensity value from 0 when it's adjacent to the light to 0 when it's directly facing the light. Now the reason why we do this is if it's directly facing the light, light will have to pass through more of the volume of the cloud, which means that it should be darker since it will get scattered much more at the center than at the edges. So that's why we're doing this, and then we're taking the maximum between 0 and negative any value that we get, if we do get, and then we're clamping it between 0.25 and 1. Now this is because we don't want even the darkest side to become completely black, because clouds, you know that we never see clouds to be completely black. They always have some sort of a light filtering out. And that's where the interesting part is, the n.l. This creates the illusion of light being filtered through the clouds and scattering in between while coming out the other end. And the next part is simple. We apply the diffuse light, and I'm also applying global transparency to it, because the more visible the cloud is, the more intensely I want to be able to show it. So it creates an interesting aspect of volume and thickness of the cloud. You can play around with it, you can remove it, it's up to you. And finally, if we're casting any shadows, we set it to true. Now if we do this, look at the viewport, you will see that the shadows are being cast onto the clouds as well. Without this, we're not going to have any shadows being cast on the cloud. This is something which you can play around with depending on where your cloud is located. If it's completely high up in the skies, like this one in my case, it's not a good idea to have this. However, if you want to have the clouds somewhere low and intersecting with your objects, then it's a good idea to have this, because it creates that illusion a little bit better. Now with all that said, keep in mind these clouds don't look that well. You'll see quite a lot of artifacts. This is because I used some off-the-shelf noise textures that I downloaded directly from Google, and the mesh that I'm using is also not specialized for this kind of particle systems, but this is something which, well, it gets the job done. It's not perfect, it's not the worst either. I will be coming back to you guys with a better tutorial on volumetric cloud generation later on in the series, but for now this is something you can get started with. It's quick, it's dirty, but it gets the work done. So I hope you liked this tutorial, and if you did, please feel free to click like and subscribe. And as always, I will be linking to the source codes in the description below. And hope you had a good day. Thank you.